more induction. And tomorrow we'll think about how some of the ways in which induction actually appears in the physical world. These are all just sort of simple abstract models for the induction that really happens in the real world, but not too simple. It's still meaningful and useful. So there's this quantity called magnetic flux, which is just a product of magnetic field strength times area. And one significant thing about this area is that the only area that counts is area through which magnetic field is actually passing. We'll look at an example of that in just a minute. And then the third factor is cosine of an angle. So imagine something like this. You've got say a loop of wire that outlines some area, and then there are magnetic field lines passing through that area. Here's a side view, and now instead, if you look from the top, look from up here, then of course all you'll see is the edge, the top edge of this loop. Here's the top edge of this loop, and then you'll see these magnetic field lines going this way if you're looking from above. And this angle theta is the angle between the axis of the loop, just a line that's perpendicular to the plane of the loop, passes right through the center of the loop, angle between the axis of the loop and the direction of the field. So there are three ways this magnetic flux thing could change. Either the strength of the magnetic field could change, or the area in which there is magnetic field could change, or the orientation of the loop relative to the field could change. In other words, this angle could change. But in any of those situations, you're getting some change in the magnetic flux. So the rate of change of magnetic flux is not zero. And whenever that happens, we saw a few examples of that in the previous video. You read about a few examples. Whenever that happens, there is a potential difference induced. A potential difference is created in that loop without adding a battery to it or without plugging it into a wall socket. Now, instead of just a loop of wire, it becomes an actual circuit with current, because when you have a potential difference, it starts pushing around current. You must have a potential difference in order to have current, but as long as you have potential difference, that's enough to give you current. But what else do we know? Any current produces a magnetic field. Every current produces a magnetic field. So this brand new induced current that wasn't there before will produce a brand new magnetic field that wasn't there before, a magnetic field above and beyond the one that was associated with the original flux. And we'll see the consequences of that in just a minute. But let's look for just 1 minute about the rate at which flux changes. As you'll see, the rate at which flux changes matters. A faster change in flux will give you a bigger induced voltage, and therefore a bigger induced current. And the brand new magnetic field will be stronger as well. And a slower rate of change in the magnetic flux gives you less induced current and less induced potential difference and a smaller new field. So let's imagine a rectangular loop, say 4 centimeters by 8 centimeters, and imagine that it's falling through a region of space that has some magnetic field up here, but no magnetic field below this line. And let's imagine you orient that loop two ways, either this way or this way, the long way or the tall way, and let the loop fall. Let's say it's falling at a speed of 2 meters per second. And when we watch in each case, when we watch the loop begin to fall, the loop that's oriented the long way starts here with half the area of the loop inside the field and the other half outside the field. And then the loop oriented the tall way starts out similarly. Half of its area is inside the field region, half is outside the field region. So even these loops have the same size and they're falling at the same speed, and yet the magnetic fluxes will actually be different in those two cases, which means different sizes of induced potential difference and different sizes of current produced. Let's look at the specifics there. So let's look at this one. We'll call it loop A. So imagine that it's, so at this point, it's 4 by 8, so there's 2 centimeters outside the loop, and then the top 2 centimeters are inside the loop. So at time 0, this is all for loop A, the area inside the magnetic field, and remember, that's the area that counts here, is what? It's just 8 by 2, or 16 square centimeters. So area times 0, and then 1 second later, this thing has fallen another 2 centimeters, so this loop is now entirely outside of the magnetic field region. So the area that's inside the magnetic field is 0. So the change in area divided by the amount of time it took to make that change, the rate of change of the area is just, well, what is delta anything? It's final value minus initial value. Final value is 0, and the initial value is 16 square centimeters, and then the time it took to make that much change was 1 second. This thing fell 2 centimeters in that 1 second. So, in this case, the rate of change in the area is negative 16 centimeters per second. Now for loop B, let's do the same thing. At time 0, just like in the case of loop A, at time 0, the loop is in this location, so half of it is out and half of it is in the field region. So this whole length is 8 centimeters, so that's 4 centimeters, and this is 4 centimeters. So the amount of area that's inside the loop right at the start is again 16 square centimeters, but then 1 second later, this has fallen 2 centimeters, so these 2 centimeters are now outside of the loop region, but the top 2 centimeters are still inside. It's now looking like that. Or here's 2 centimeters and then 6 centimeters outside. Well, it's falling. So now, after 1 second, the area inside the loop is not 0 like it was for loop A. It's 2 times this width, which is 4, or 8 square centimeters. So again, what's the rate of change in the area? This is final minus initial value, as always. The final value now is 8. and the initial value was 16, just like before, divided by 1 second. So in this case, the rate of change is just minus 8 square centimeters per second. In other words, the rate of change in the area here is slower than it is here, only half as fast here as it is here. Here, the area is changing faster. What's the significance of that? This. A change in flux, in this case, is not coming from any change in the field strength, and it's not coming from any change in the orientation of the field and the loop. It's coming from a change in the area, and for loop A, the area changes faster, or the rate of change that this number has is bigger for loop A than it is for loop B. So this number changing at a faster rate, right, we're not so much interested in the fact that these changes are negative changes, decreases. We're interested in just how fast it changes. This changes faster, which means the flux changes faster for loop A than it does for loop B. And as a result, more change, or faster change, means more induced current and more stronger induced voltage in case A, and a smaller induced potential difference for loop B, and therefore a smaller current for loop B. All right, now let's look at a few more examples. This just takes some getting used to. Let's say it's got some magnetic field all pointing perpendicular to the blackboard and pointing at us. And then there's a circular loop perpendicular to the field. And let's say that new field is getting stronger. So that factor is increasing as time goes by, so there's a change in the flux, which means there's going to be induced potential difference, and that will create a brand new, or as we call it, induced current. Well, the question is that new current going to go counterclockwise or clockwise? And one of the things that you read about most recently, Lenz's law, tells us which way that current has to go. And the idea goes like this, that that induced current produces, or that induced potential difference, produces a new induced current, and like any current, this produces a magnetic field, a new magnetic field that wasn't there, a new magnetic field above and beyond this one. Now, what direction does that new magnetic field point? That Lenz's law tells us the direction of that new magnetic field, tells us what the direction of that new magnetic field must be. And once we know the direction of that field, we can use the thumb finger right hand rule to deduce what kind of current we had to have in order to produce that particular kind of field. Lenz's law tells us that this new current or sorry, this new field causes some new flux that wasn't there before. And that new flux always counteracts, tries to undo or counteract whatever original change in flux got this whole process started. So the original change in flux is what? We can characterize it this way. Outward flux, just call it outward flux because it comes from field lines flowing outward, flowing out of the plane of the blackboard. Outward flux increasing. So this new field creates new flux, and the new flux has to sort of counteract or undo this change. So the new flux has to point inward in order to counteract or subtract away the increasing flux that flowed this way. And whenever we talk about outward flowing flux or inward flowing flux, here's something to remember. You won't get anywhere if you don't remember this. Remember this. This always refers to what's happening inside the loop. Whatever's happening outside the loop is irrelevant. Don't bother with it. It doesn't matter. What matters is what's going on inside the loop only. So in order to get new flux inside the loop, that means the new magnetic field, which causes that new flux, has to point inward in order to get new flux inward. So inside the loop, the new field points that way. Now that we know the direction of the new field, we can figure out which way the induced current has to flow in order to get field pointing that way inside the loop. What's inside the loop matters. Remember this rule: thumb in direction of the current, and our fingers will curl in the direction of the magnetic field. So we want inside the loop magnetic field pointing this way, inward. So that means clockwise current. The new current, the induced current, has to be clockwise. Because if you let your thumb go in the direction of clockwise current and then curl your fingers, at points inside the loop, your fingers will be pointing into the paper, into the blackboard. Remember, in a loop, in a current loop, the field lines make loops perpendicular to the plane of perpendicular to this plane, and so if the current is clockwise, then inside the loop, those loopy field lines will be going this way, and then outside the loop, those loopy field lines will be coming out like this, and then circling around and coming in when they get inside the area of the loop. So, long story short, this means that the induced current must be flowing clockwise. Okay, let's look at a slightly different example here, just slightly different. Let's say this was for this kind of field getting stronger. Let's just take the opposite case. The original field, instead of getting stronger, is now getting weaker. So again, there's a change in flux. And our first step is to characterize that change in flux. And we can say, in this case, outward flowing flux is getting weaker as the field lines are going this way, and the strength of the field in this direction is getting weaker. Outward flux decreasing. So that means the new flux caused by the new field has to counteract this. So the new flux must be pointing outward to add back some of the outward flux that disappeared. And flux in that direction, of course, more stronger additional flux in that direction happens because there's more stronger additional magnetic field in this direction. The new magnetic field points out this way. And what kind of current, clockwise or counterclockwise, what kind of current in that loop, what kind of induced current, in other words, will give us this kind of field? Well, we want field inside the loop. Remember, always, it's what's inside the loop that matters. We want field inside the loop pointing this way, and we'll get that if we have counterclockwise current. Let's use this rule. Imagine letting your thumb move counterclockwise so that it's always moving along with that counterclockwise current. And then as you can see, for all points inside the loop, when you curl your fingers to show you the flow of the loopy field lines, inside the loop, your fingers will always be pointing out, indicating that the new magnetic field caused by this induced current is a field that inside the loop points out just the way we want it to. So that means that in this case, the induced current is counterclockwise. Okay, now another example. You just have to try lots of these examples until you feel comfortable with it. There's no reason you should expect to feel comfortable with it the first time. You just have to keep trying. Let's take kind of the opposite situation from what we've been looking at before. Here's another region of magnetic field like this. And then you've got another rectangular loop that's falling. And so at the moment you start watching, the top part of the loop is outside the field region, the bottom part of the loop is inside the field region, and as time goes by, more and more of the loop area is inside the field region. Or in other words, this number is increasing. Remember, it's area where there is field that is what we're referring to with this particular A for area symbol. So the flux is flowing this way, because the field lines are flowing this way, and flux outward is increasing. That's the kind of change that we're in flux that we're getting. Flux outward is increasing. Okay, and that outward flux is increasing. So a change in flux means there's an induced voltage, and that produces an induced current, which produces brand new magnetic field. The brand new magnetic field produces some new flux, which has to counteract the change. You're getting increasing flux this way, so you want to decrease that. you want to subtract away some of the increasing flux this way, which means you want the new field to point inward. Inside the loop, you want the new field to point inward, which gives some flux flowing this way, which will subtract away the increasing amount of flux flowing the other way. So that means the new field points inward, and what kind of current in the loop will produce new field inward? Well, it's just like an example we saw a few minutes ago. Clockwise current. Induced current is clockwise. Remember the right-hand rule that connects current direction to flow of the field lines. So if your thumb moves around following a clockwise current, your fingers will always curl in the same direction as the field lines flow, which means inside the loop, your fingers are curling towards the loop, your fingers are curling into the plane of the blackboard, which means inside the loop, that new field produced by this induced current points into the loop. That's the kind of current we need to get that kind of field. That's the kind of field that we need. That's the kind of field that is required to counteract this change. Now, as we'll see later, the new field and flux must counteract the old original change in flux because the law of conservation of energy is true. You'll have an assignment the next day or two where you go through the steps to see why conservation of energy requires that the new field act like this to counteract the original flux change that got this whole process started. You'll find that if the new field didn't work this way, you'd have an explosion of energy coming out of nowhere, which, according to the law of conservation of energy, does not happen. But anyway, the idea here is that you don't have a source of voltage, a source of potential difference, but you can produce a potential difference just by having other things move around. Right? In this case, it's just having the wire move. So when you've got the induced current going this way, it's just as if you had snuck a battery into this circuit, and the battery would be oriented, would have polarity like that, right? The long line represents the high potential, the low line represents the low potential, and remember that electric field always points from higher towards lower potential. So inside the loop, electric field lines will always be flowing clockwise, and so force on a positive charge points the same way as electric field, so positive charges will always feel a force pushing them clockwise, and whenever we imagine current, we imagine conventional current. In other words, we imagine the motion of positive charges, even though we know it's really electrons in most cases. And of course, those positive charges then will be pushed in the same direction as the electric field, because they are positive charges. Essentially, getting current to appear because you've made a potential difference appear is essentially how every sort of power plant works. That whether it's coal or gas or nuclear or a windmill or geothermal or or hydroelectric, whatever, you either burn some kind of fossil fuel or let the wind spin the blades of the windmill, or let the falling water in the hydroelectric power turn the blades of some kind of turbine. You do all those things in order to get something moving, right? You burn fossil fuels to produce steam, and that steam under higher pressure pushes on the blades of a turbine, gets those things moving, and that in turn makes something that is sitting inside a magnetic field spin around. And because it's spinning around, right, this factor is changing. So flux is changing. And whenever a magnetic flux is changing, you get a new induced current that wasn't there before, and then that's the electric current that is sent out along the power lines. Okay, that's enough to ponder for right now, and now you can try some of the exercises.